let's talk about math again. Today I would like to talk about incidence geometry. It's very relevant to my research, and I want to talk about a certain proof by Jacques Tits that is a little bit tricky, but I find it very interesting and it's also very important for my research. And it's the proof of the theorem that projective planes in rank 3 polar spaces are Moufang. And that is the topic for today. I am recording this on several different days because recording for me can get quite exhausting. I find it very different from giving a talk, because when I give a talk I can see an audience listening, paying attention, and then I pay attention as well. But when I sit alone in a room talking to a camera, I sometimes stop paying attention, and then I say things wrong and have to say them over and over again, and then I'm extremely exhausted at the end. So now I'm trying to do it on several different days. Which also leads me to my disclaimer. It can always happen that I say wrong things, and please think for yourself and question everything I say. The Tits proof I want to talk about today is the original proof by Tits is only like half a page long, and when I wrote it down in all detail it was 6 pages. I tried to come up with all the little arguments that I didn't find as trivial as Tits did. But of course it can be that maybe I misunderstood something or one of my arguments is false. So that's why think for yourself and question everything. If you would like to read through the original proof by Tits, you can find it in Buildings of Spherical Type and Finite BN Pairs by Tits. And the points, lines and planes will have the exact same names as in this video. So the whole notation will be the same, so that you can really compare if you would like to. If you are otherwise searching for literature about incidence geometry and polar spaces, I find it very difficult. I needed a long time to find some literature that was helpful to me. Actually, I complained so much that people listened, and maybe at the end of next year, hopefully, there will be a nice book about polar spaces coming out. But let's see about that. At the moment, I can refer you to the Handbook of Incidence Geometry. It's a very large, thick book by Buekenhout. I don't know how to pronounce the name correctly. I don't know how to pronounce any name correctly. There's also another book by Buekenhout and Cohen called Diagram Geometry. I find that very helpful. There's a book called Points and Lines by Ernest Shult. I really like the writing style of that book. I find the Points and Lines books very friendly, even though the theorem we will prove in this video is also proved in that book, but the proof in that book is not fully working out. So be aware that don't trust this proof maybe. And then otherwise it's already difficult to find anything else, but Hendrik van Moldegem published like so many papers about polar space stuff. So you can go to his webpage and scroll through the almost 300 papers, and maybe there you can also find some things about polar spaces that are helpful. I will now give a very brief introduction and say what a projective plane is, what a polar space is, what the Moufang condition means. If you know all that, I have everything time-stamped and you can just skip ahead. So incidence geometry is all about points and lines. It makes a lot of sense that Ernest Shult called his book Points and Lines. And one can define what a point-line geometry is. And it's quite simple, and I think the most difficult part is to not overthink it. So a point-line geometry is just, we have a set of points and we have a set of lines and we have a relation that tells us which points are on which line, basically. It tells us whether 2 lines have a point in common, so which lines intersect, and it tells us which points are together on one line. So we also say when 2 points are together on a line, we say they are collinear. And what we want is, from our set of points, lines and the relation, that every line has at least 2 points and 2 distinct lines never intersect in all of their points. And when we have that, a set of points, a set of lines, something that tells us about the relationship of the points and lines. If we have that every line has at least 2 points and that there are no repeating lines, then we have a point-line geometry. Now there are different kinds of point-line geometries. A point-line geometry itself does not have that many properties, but we can add certain properties and then we can get different kinds of point-line geometries. For this video, the most important ones are projective plane and polar space, and I will talk about them now. So a projective plane is a point-line geometry such that every 2 lines intersect in a point. We can always find a connecting line between 2 points, and there exist at least 4 points for which any 3 are non-collinear. The first condition is for every 2 lines in the plane we find an intersection point. The second condition is for every 2 points in the plane we find a connecting line. And the third condition is not for all points and lines in the plane. It just means there exists at least 4 points for which it is the case that if you pick out any 3, then they are not on a common line together. It just means that in the whole plane, somewhere there exists a quadrangle, basically. Because if you imagine a quadrangle, it's the easiest example, and you pick out any 3 points, so any 3 of the vertices, then they are not on a common line together. And that is a projective plane. When it comes to polar spaces, it's a bit tricky because many different authors have many different ways of defining a polar space. I will give the definition that I myself find the easiest, and it will be okay for this video. It will actually be a little bit different than how Tits defines it in his lecture notes, but the 2 definitions are completely equivalent, so it's all fine. For us in this video, a polar space will be the following. A polar space will be a point-line geometry such that every line has at least 3 points. There does not exist a point in our space such that this point is collinear to all of the other points. And if we have a point and a line, and the point is not on the line, then the point is collinear to either exactly 1 point of that line or to all points of that line. So you have a point and a line, the point is not on the line, and then we either have exactly 1 line between this point and some point of that line, or we have lines between all points of that line and that point. This is also called the one or all axiom, and it's very important and we will use it a lot. The second condition that I mentioned, that there does not exist a point that is collinear to all the others, this is sometimes left out in definitions of polar spaces, and when it's left out you can differentiate in degenerate and non-degenerate polar spaces. The non-degenerate polar spaces are then the ones where there does not exist a point that is collinear to all the others, and the degenerate polar spaces are where there might exist a point that is collinear to all the others. There's also another condition that we would like our polar spaces to have, and it is that any chain of singular subspaces in the polar space is finite, and it might not be clear what that means right now. I will give you a little fun fact. If we have a polar space, then we can find lower dimensional projective spaces in this polar space. And we actually define the rank of a polar space as being 1 more than the highest dimension of a projective space we can find in the polar space. So, for example, if we have a projective plane in a polar space and there's no higher dimensional projective space in this polar space, then the dimension of the plane is 2, so the polar space would have rank 3. And singular subspaces, the projective spaces we have in this polar space, are also called singular subspaces. So what does it mean that any chain of singular subspaces is finite? It means, for example, if we have like a point, the point is on a line and the line is on a plane, if we were to go on like that, we would not go on forever. Like this chain should always be finite. And now I already mentioned the rank of a polar space, So in this video we will mostly talk about rank 3 polar spaces. The thing is that projective planes in polar spaces of rank higher than 3 are Moufang is kind of trivial, because we know that projective planes and projective spaces are Moufang. And now if we have a polar space of rank higher than 3, then we know that we find projective spaces inside the polar space that have a higher dimension than the projective planes. And so that the projective planes would be contained in a projective space inside the polar space. And then the result follows from the fact that projective planes and projective spaces are Moufang. So that's why in this video we focus on rank 3 polar spaces, because in that case everything is not as clear. Suppose we have a polar space of rank n. We will call this polar space thick if for any singular subspace of dimension n-2 it is contained in at least 3 singular subspaces of dimension n-1. Let's visualize that. It means that a point is on at least 3 lines. A line is in at least 3 planes. That's all for our rank 3 case for now. So, but it goes on like that. So the, a smaller thing always contained in 3 and 1 bigger things. I also want to make clear how I use certain words. So I've already used the word collinear with 2 points. So if we have 2 points, we call them collinear if they are on a common line together. When I say that a point and a line are collinear in this video, what I mean is that the point is collinear to every single point of that line. When I talk about the perp of a point, I mean the set of all points in the polar space that are collinear to that point. When I talk about the perp of a line L, I mean the set of points such that they are collinear to every single point on that line L. And these are very important words and I will use them a lot. If we are in our rank 3 polar space and we have projective planes in that polar space, then we can define maps using this perp thingy. What I mean is, if we have a plane P and a point X, and we look at the perp of X, so we look at all points that are collinear to X, and we intersect this perp of X with the plane P, then that should be, what we get then, should be the projection of X onto P. That only works well when X is not on P, because otherwise we just get the whole plane P and that's not very interesting. We can also do that for lines. So if we have a plane P and a line L that is not on P, we can look at the perp of L, so the set of points that are collinear to all of the points on L, and intersect it with the plane P, and what we get then is the projection of L onto P. We will call 2 planes A and B opposite if there does not exist a point A and A such that B is contained in the perp of A, and if there exists no point B and B such that A is contained in the perp of B. If this is given, then we call the planes A and B opposite, and that is a very important notion that we will also use a lot. It means that there exists no point in the plane A that is collinear to all of the points of the plane B. And it means that there's no point in the plane B that is collinear to all of the points of the plane A. Now, in a rank 3 polar space, if 2 planes do not intersect, that already means that they are opposite. Why? Because if we had a plane and then a point that would be collinear to all of the points of that plane, then we would already get a higher dimensional projective space, but that does not work in a rank 3 polar space. So for dimension reasons, in a rank 3 polar space it is the case that 2 projective planes are opposite if they do not intersect. If we have 2 opposite planes and we take a point in the one plane and project it onto the other, we get a line. if we take a line in the one plane and project it onto the other, we get a point. So if we have opposite planes and look at the projections, then points map to lines and lines map to points. And the projections are actually isomorphisms. And that is very nice and very important. Also, if we imagine we had 4 opposite planes and we would start with a point, we would get a line, a point, a line, a point. Or if we started with a line, we would get a point, a line, a point, a line. So that works very nicely. And I can refer you to some literature. I will not prove that right now. We will also use a theorem that I will not prove that says that if we have a point and a plane such that the point is not on the plane, then we can look at the projection of that point onto that plane, and then we can look at a subspace that is generated by that point and the projection of that point onto that plane, and that actually gives us a unique projective plane that contains that point and intersects the plane. We can do the same for a line. If we have a line and a plane such that the line is not on the plane, we can look at the projection of that line onto that plane, and then we get a unique plane containing that line and intersecting that plane. I will state another fact that we will use, but that I will not prove right now, and it is that if we have 2 planes in a polar space, we can always find a third plane that is opposite to both of them. If we are in a polar space and we find a set of pairwise collinear points, then we already know that they are contained in a plane. That is also another basic fact. I am aware that now at the beginning I'm giving you many properties and facts that you just have to believe, I guess, or look up, and that I'm not getting into, and maybe I should, but this video is already extremely long because explaining the proof of Tits takes a long time. So I just wanted to make this introduction very short. Suppose we are in a polar space and we have a point P, and we want to define a new point-line geometry, and we say that the set of points should be the lines through P. So for every single line that contains P, we have a point. And we say that we draw a line between 2 points if the lines are contained in a common plane together. So we are only looking at the lines through P, and if some of the lines are in a plane together, we connect them by lines. It's easier to see in an example if you look at pictures. But this new point-line geometry that has its points, all the lines through that point, and we draw a line between points here if in the original setting the lines are contained in a plane together, then this new point-line geometry is also called the residue of P. And what is very helpful is that these residues are again polar spaces. And of course this should be proven. I will not prove it right now, but this is a very useful concept and we will also use it. If you want to know more about residues, sometimes you can also find what is quite similar are quotient spaces of polar spaces. You can also read about them. So quotient spaces and residues. Also the word quotient space you already kind of get the impression that this is a polar space again, so that's nice. Now suppose we have a projective plane. Pick any arbitrary line in that plane. We will call that line L. Then pick any 2 arbitrary points in that plane, B1 and B2, that are not on L and that are distinct from each other. We know that we can find a connecting line between B1 and B2. And we know that this connecting line will intersect the line L in a point. This point we will denote by A. Now suppose we find an automorphism of the plane that fixes the line L pointwise, that moves the point B1 to the point B2, and that fixes every line through A line-wise. then that is a very nice automorphism of that plane. And if we can do that, because we said the line L is arbitrary, the points B1, B2 arbitrary, everything arbitrary, if we can always find such an automorphism, then the plane is called Moufang. That is the Moufang condition. If we are in a situation that we have a plane and an automorphism and a line L such that under the automorphism this line is fixed pointwise, then we call L the axis of this automorphism. And if we have a point in the plane such that under this automorphism every line to that point is fixed line-wise, then we say this point is the center of the automorphism. Now, if we have a projective plane and an automorphism of that plane, and this automorphism has an axis and a center, and it happens to be the case that the center is a point on the axis, then we also call this automorphism an elation. So for the Moufang property, we need that for every single line L in the plane, the group of elations, and one can actually show that the set of elations for a projective plane forms a group, if the group of elations acts transitively on all of the points of that plane except the ones that are on L. So we actually still need to be able to move things around despite the fact that one line gets fixed pointwise and many lines through a point gets fixed line-wise, but because they are only fixed line-wise and not point-wise, we can move the points around. And that is the transitivity that we want. We have to be able to move points around outside the axis. Now, I told you that if we look at two opposite planes, then the projection gives us an isomorphism. So the goal is, in order to show the Moufang property, to find different planes and project and go back to our original plane and then get an automorphism of that plane that gives us the properties that we need. The theorem that we want to show is that every projective plane in a thick non-degenerate polar space of rank 3 is Moufang. Let S be a thick non-degenerate polar space of rank 3 and let M be a projective plane in that polar space. We want to show that M is Moufang. Therefore, we have to show that there exist automorphisms that have the nice properties. And we do that by constructing some other planes, and then we show that if we go from this plane and project onto another plane, onto the other plane, and back to M, that we then get an automorphism that has the nice properties. And for the automorphism, in the end, we actually only need 4 planes. We need M itself, then another plane that intersects M in the axis, or like in a line that later turns out to be the axis, and then we need 2 planes that are both opposite, both A and M. And then we go from M to one of the opposite planes, to A, to the other opposite plane, and back to M. But we can't just have like random opposite planes. They need certain properties in order for the automorphisms in the end to have a center. So what happens in the proof is that we actually have 6 planes, but 2 of them are just helper planes. They are not relevant for like the automorphism in the end. We don't project onto them, but we need the 2 helper planes in order to construct the 2 opposite planes, because the opposite planes can't just be random opposite planes. They need certain properties, and we get these certain properties by like finding a very good construction, and for the construction we need the helper planes. It's all a bit tricky, but yeah, that's what we want to do. Okay, we have our projective plane M in our polar space. Now, take an arbitrary line in M. We will call that line L. Then we know, because we are in a thick polar space, that this line L is in at least 3 planes. So we easily find another plane A such that M and A intersect in the line L. Let B1 and B2 2 arbitrary points in M that are not on L. Later, when we define the automorphism, we want to show that the automorphism has axis L and moves B1 to B2. And now let's look at the connection line between B1 and B2. It has to intersect L in a point, and let's call this point A. Later we want to show that A is the center of our automorphism. So we have our plane M and our plane A, and we have our point little a, which is in both M and A, and the planes M and A intersect in the line L. Now we want to look in the residue of the point A. In the residue of the point A, we can see the line L as a point, and we can see the planes M and A as lines. So the residue of little a basically looks like this. We have a point that stands for the line L, and we have two lines that stand for the plane M and A. And obviously these lines also have points. And now we know that the residue of a point is again a polar space. And if we are in a thick polar space, the residues are also thick polar spaces. So we know here that we can find a line opposite to both the lines that stand for the planes M and A. We can find a line opposite to both of them in the residue of A. Now we will call this line in the residue of A B. And now if we go back to our original picture in our original polar space, what does this look like now? We know that B is opposite to both M and A, but it's also contained in the residue of A. That means B has to be a plane that contains the point little a, but otherwise it does not have anything in common with M and A. So we have M and A, and then the plane B is basically only hanging on there, intersecting M and A only in the point little a. And that's how we construct the plane B. So now we have three planes, M, A and B, and we have the 2 points B1 and B2 that are only in M and not in any of the other planes we have so far. So what we can do now is we can look at the projection of B1 onto B and the projection of B2 onto B, because we know that if we have a point and a plane such that the point is not in the plane, we get a unique plane that contains the point and the projection of that point onto that plane, which is a line. So the projection of B1 onto B is a line, and the projection of B2 onto B is a line. And since B1 is collinear to A and B2 is also collinear to A, and the point A is contained in B, we know that the projection of B1 and the projection of B2 onto B has to be a line through A. And now assume that the projection of B1 onto B is a different line from the projection of B2 onto B. Then let's look at the projection of B1 onto B and take like an arbitrary point on that line. Then we already know that this point is collinear to A because it's a line through A, and collinear to B1 because it's the projection in the projection. So this point is already collinear to B1 and A. So it has to be collinear to all points on the line B1A. In particular, it has to be collinear to B2. And that is the case for every point that is on the line that is a projection from B1 onto B. So every single point of the projection of B1 onto B has to be collinear to B2. But that means that the projection of B2 onto B already has to contain all of these points. So the projection of B1 onto B is contained in the projection of B2 onto B. And if we switch around the numbers, 1 and 2, then we also get that the projection of B2 onto B is contained in the projection of B1 onto B. But since the projections have to be lines, we already know that the lines have to be the same. The projection of B1 onto B is the same line as the projection of B2 onto B. So we have a line in B that is the projection of B1 onto B, but also the projection of B2 onto B, and it is a line through A. Now let C be a point on that line that is not A, any other point. So the point C is a point in B that is not A. So the point C is not in M, and the point C is also not in A. So we can now look at the projection of C onto A. and again we get a line, and because C is collinear to A and A is also a point of A, we know that we again get a line through A. So the projection of C onto A is a line in A through A. Suppose the projection of C onto A were the line L. Then the projection of C onto M would also be the line L. But C is part of the line that is the projection of B1 and B2 onto B. That means C already has to be collinear to B1 and B2, but B1 and B2 are not on L, so that would be a contradiction. So what we now found out is the projection from C onto A is not the line L. It is a line through A, but not the line L. Now let D be a point that is on the line that is a projection of C onto A, that is not the point A. So we have a line that is a projection from C onto A, and this line has to go through A, and now we want to pick another point on that line that is not A, and we call that point D. So now we can describe the projection of C onto A as the line AD. And since the projection of C onto A is not the line L, we already know that D is not on L. Since the point D is in the projection of C onto A, we already know that C and D are collinear. That means there's a line between C and D. And this line is contained in the plane ACD, but we know that every line has to be in at least 3 planes. So let C be another plane that contains the line CD that is not ACD. So C is a plane that contains the line CD, but not the point A. It's a different plane. Next, we want to argue that the points B1 and B2 are not contained in C. And we do that by showing that B1 and B2 are not collinear to the point D. Okay, so suppose B1 and D were collinear. Then we could look at the unique plane containing B1 and the projection of B1 onto A. Then the projection of B1 onto A contains the line L, since B1 is collinear to every point on L and L is contained in A, but it would also contain the point D. So then this plane would contain B1, L and D. But the plane M, we can write it as just generated by L and B1, and the plane A we can write as the generated by L and D. So now if B1, L and D are in a common plane together, that already contradicts the fact that the intersection of M and A is only L. Therefore, B1 and D can't be collinear. And the same argument works for B2. So now we know B1 is not collinear to D and B2 is not collinear to D. Therefore, the points B1 and B2 can't be contained in C, since the plane C contains the point D, and if, like for a plane, we know that there are connecting lines between all the points. So this would not work out. So now that we know that the points B1 and B2 are not contained in the plane C, we can look at the projection of B1 onto C and the projection of B2 onto C. And we know that the plane C contains the point little c. And little c was a point in the projection of B1 onto B and a point in the projection of B2 onto B. That means C and B1 and C and B2 are collinear. C is also a point of the plane C. So the projection of B1 onto C and the projection of B2 onto C has to contain the point little c. So we get lines in the plane C through the point little c. So little c is a point of B. So we could ask the question, is the projection of B1 onto C already contained in the plane B? Suppose that were the case. Then the projection of B1 onto B would be the same as the projection of B1 onto C. But the projection of B1 onto B contains the point A. And the plane C was defined as a plane that contains the line CD different from the plane ACD. In particular, the plane C does not contain the point A. Now, if the projection of B1 onto B were the same as the projection of B1 onto C, then C had to contain the point A, and that is a contradiction. So, and the same works for B2 again. So now we know that the projection of the BI onto C is not contained in B. So the point little c is the only point in the projection of BY onto BI onto C that is also in B. Also note that the projection of B1 onto C and the projection of B2 onto C are not the same line. Suppose they were the same line. So suppose we had a line CE. That would be the projection of B1 and also the projection of B2. Then every single point of the line CE would already be collinear to B1 and B2. So it had to be collinear to all points of the line B1, B2, but that includes the point A. But then A would be collinear to EI. But then A would be collinear to C and EI, so to the whole line CEI, and then the projection of A onto C would have to be CEI. But the projection of A onto C is already the line CD. And also EI and D have to be distinct because BI is collinear to EI but not to D. So that would be a contradiction then. So now we know that the projection of BI onto C is a line in C that goes through the point little c, which is also contained in B, but that this is the only point that is on the line that is a projection from BI onto C that is also contained in the plane B. That means if we pick an arbitrary point on the line that is a projection of BI onto C that is not the same as the point C, then we already know this point is not contained in the plane B. Okay, let's do that. Let's pick an arbitrary point on that line that is not the point little c, and we call that point EI. Then EI is not contained in the plane B. That means we can look at the projection of EI onto the plane B. The projection of EI onto B is a line in B, and it contains the point little c, since C and EI are both on the line that is a projection of BI onto C, and C is also contained in B. And the unique plane that we get, that is generated by the point EI and the projection of EI onto B, contains EI, contains this line that we get in B, so the point little c, and it contains the whole line that is a projection of BI onto C, and we name that plane DI, and we name the line that is the intersection of DI and B, so the projection of EI onto B, the line through little c, this line we call HI. Now we want to show that the planes D1 and D2 are both opposite to both M and A. So suppose there were a point P in the union of the planes M and A that were also collinear to all points of DI. Then the point P were collinear to A, it were collinear to the lines CFI, so the lines where the plane DI intersects B, and also A were collinear to all of CFI because A is also contained in B. But then that would mean that P, A, and the lines CFI were pairwise collinear, so they would have to be in a common plane together. But then the plane DI can be written as generated by P, C, and Fi. That means A would already have to be in DI. But if A were in DI, then A would be collinear to EI, and that would be a contradiction again. And that's why the planes DI for I equal to 1 or 2 have to be both opposite to both M and A. Now we want to define a map alpha I from M to A that first is the projection onto DI and then the projection onto A. So we get alpha 1 and alpha 2. And we define the map alpha from M to M as alpha to inverse of alpha 1. So we go from M to D1 to A to D2 to M. And now we want to show that alpha is an automorphism of M with axis L and center A that moves the point B1 to the point B2. Let's do the easy things first. Let's look at the line L. We want to show that L is an axis of this automorphism. That means we want to show that L is fixed pointwise under this automorphism. So, first let's project the line L onto the plane D1. Then we get a point. We don't know much about this point, but we get a point. And we already know that every single point of the line L is collinear to this point. So now if we project onto A, and the line L is also contained in A, we again get the same line L. And the same when we project to D2 and back. So we already know that the line L is fixed. Also, if we pick out a particular point, little l on that line L, then we get a line in DI, and we already know that every single point on that line is collinear to little l on L. And if we then project to A, then this point is also contained in A, so we get the same point again. So the line L is definitely an axis for this automorphism. Now we want to see that the point B1 gets moved to the point B2 under this automorphism. So first we project B1 onto the plane D1. Then we get the line CE1. So this is the projection of B1 onto D1. And this equals the projection of B1 onto C. The point CE1 was contained in the plane C. Now the plane C also contains the point D. So we already know that every single point of the line CE1 is collinear to the point D. The point D is contained in A. So we know that the line CE1, if we project it onto A, we get the point D. So the projection onto A of the projection of B1 onto D1 is the point D. Now if we project the point D onto D2, we get the line CE2, since CE2 is a line in C and also contained in D2. But then this line, if we then project onto M, goes to B2. And that means we did the whole round. We get that B1 is mapped to B2. So we also checked that. Now we want to show that the point A is the center of this automorphism. So first of all, A is a point on the line L. So we already showed that A is fixed pointwise, so that is good. We can also look what A maps to, and if we look at the projection of A onto DI, we get the line HI, since A is a point of the line of the plane B and HI is a line of the plane B. So in particular, A is collinear to every single point in the plane B, including all the points of the line HI. So if we map A to DI, since M and DI are opposite planes, we know that the point A has to map to a line, and this line already has to be HI. So A maps to H1, maps back to A, maps to H2, maps back to A. Now let X be an arbitrary line in M through the center A. We want to see that X is fixed as a line. For that we look again in the residue of A. There we can see the planes M and A as two lines and the plane B as another line. And now in the residue of A, the line X is a point on the line M. And we know that the line M and the line B are opposite. That means there exists a unique point on the line B such that our point x is collinear to that point on B. And if we again take this point, we know that it's collinear to a unique point on the line A. So we have 3 points here, and let's call the point that x is collinear to on B x prime, and the point that x prime is collinear to on A x prime prime. Then we know that in the residue of A, x projects to x prime projects to x prime prime. If we now go back to our original space, then x prime corresponds to a line in B through the point little a, and x prime prime corresponds to a line in A through the point little a. And now if we project the line x onto the plane D1, then the point that we will get is the intersection point of x prime and h1, because h1 was the line in the intersection of D1 and B. And now the point will then continue, if we project onto A, will continue mapping to the line x prime prime. If we now go with alpha 2, the line x will map to the intersection point of h2 and x prime, and this will map to x prime prime again. So no matter if we go with alpha 1 or alpha 2, the image of x in A will be x prime prime. And now the map alpha was defined as the composition of alpha 2 inverse and alpha 1. So alpha 2 inverse of alpha 1 of x is alpha 2 inverse of x prime prime, and that is again x. So now we have shown that the lines through A are actually fixed. And so the line x was not equal to L, but we've also already shown for L that it is fixed, so this is all good. I really hope that was somewhat understandable. Like I said, the original proof by Tits is only like half a page long, so I tried to add a lot and explain a lot and fill in the tiny little gaps. And yeah, I hope it helped maybe a little bit. If you always wanted to understand that proof by Tits, maybe now it's a bit easier. I really hope so. So thank you for watching if you watched until this point, and goodbye.